potential research project is heat capacity of ruthenium trichloride thin film. And heat capacity, well, in gases, in our thermodynamic class, we will speak about, you know the subject, like heat capacity for gas at constant volume or constant pressure, CP/CV. For solids, it's hard to define volume and pressure and imagine that some of them are changing. So we're not going to put this subscribe. So just change of energy in temperature. And to find the energy, how can we do it? In your previous life, in your previous part of the course. So one takes the statistical weight of a certain state, multiplies it by the energy of the state, and makes summation over all states, right? And I think it is what you covered with Professor Bruchhaus, right? Then one just plugs this stuff in here, takes derivative, and reports what how heat capacity depends on temperature, right? And we expect that for this magnetic material, it will be growing, then spike, and then continuous growing, and this will be Curie temperature. So why? And I'm respecting your intellectual strengths and my intellectual strengths. Why this simple problem can be counted as a graduate project? What's challenging? The energies for system of spins. So it is, if it is ruthenium 3+, it can be considered that each ruthenium is just one spin which can be up or down, right? So it's quantum system. And also I'll forget about chlorines and put only ruthenia, which will be in the centers of the honeycomb. So it will be triangular lattice. So each point is ruthenium, and one can continue it same as graphene, yeah. But now those are ruthenia, and at each point there is a spin which can be up or down, and I can count each point here. Let's say I equals 1, 2, 3, 4, 5, 6, and so on. Then how can we get the energy of the state? Number 1. So we have count of sites of ruthenium atoms, and we need energy of a state of a system when all spins take a certain configuration. So if we have just one spin, which can be up or down, how many possible states will be? 2. Okay, now if I have 2 spins, one spin that can be up or down, and second spin up or down. So number of states, 1 or 2. Here, how many states for 2 spins?
3. Wait.
Try once again. What are your 3 states?
4.
Yes. Well, I shouldn't say yes or no. Please argue. Crystal, why 3?
No, I'm further because it was up, 2 that are up, down, just vice versa, but they're not identified, so you can't say one or the other, and then 1 down.
Okay, so you subtracted the degeneracy, but if you count these degenerate states as 2 different states, then 4, right?
Yeah.
So you would agree with John. So 4. Now, if I have 4 spins, if I put like atoms 1, 2, 3, 4, how many states of this spin configurations will be?
4 times 3 times 2 times 1, 4, 12, 24.
So guesses are 24. What are other options? Just so.
Oh, sorry. I'm just trying to.
I have my own answer, and it is different from this. No. So options are 8. What are other options? So let me probably will slow down, but it is a fun stuff that you may like. So I will. No. So let's play that each of us is a little computer in the digital bits. So instead of putting arrows up and down, I will put zeros and ones. So all 4 down, I put 0, 0, 0. All 4 up, 1, 1, 1. And now I start 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0. If you can continue table, can you count how many? 16. Yes, correct. Okay. No. Why I'm talking about 1, 2, 4, and next one I will offer probably 9, because it is a 2-dimensional lattice, and I count like a square with certain size, like 1, 2, 3, 1, 2, 3. So next one will be 9. If you have 9 spins, what will be the total number of states? 2 to the 9. Which is? I know the answer. I'll write it down and you tell. 512. Yes. Make sense? You agree with this? No? Okay. So next one will be 16. $65,536. Okay, and I will count it as, so you already got the idea. It is 2 to the power of this number of sides. So 2 to the 16 is 2 to the 10 times 2 to 6. So 2 to the 10 is very easy to remember. If you play with computers, you know it without counting. Yeah, but approximately 1,000, 10 to the third, right? And 2 to the 6, 64, right? So approximately 64,000, right? And just for curiosity, if you take the size,
5,536.
Correct. I think you and John agree on that. Yep. Maybe one day we need to move to another class which has several cameras that follow each one, and we have those. And it is fun to operate, and maybe we'll take shares. Someone will be moving camera and focusing on someone. I tried it well, but talking about and focusing camera is a little bit too much, but it's fun. And maybe 209 is available at this time, and then it's a good modern classroom. So next one, 25. 2 to the power 25 will be 2 to the power 10, 2 to the power 10, 2 to the power 5. So will be 1,000 times 1,000 will be a million, times 2 to the 5 will be 32. 32 million, right?
Yeah, 33,554,432.
Thank you. Now, so after you see that this project is, maybe the equation is quite simple, but implementation, the number of terms in this summation will be quite big. So I'm not going to ask you to do it by pen and paper. It will be some computation, right? Now, you already see that the project is challenging. What is the energy of the state? So if we have index I for the state, and then we have so many spins, so maybe spin number 1, spin number 2, spin number 3, spin number whatever we have number. So energy does depend on state of all of the spins, right? And so it is as many indices as many spins, and the actual there is a formula for this which is quite simple. So it tells that this energy will be summation. Maybe we'll use Greek, like S mu and S nu, and then spin mu times spin u with some constant, right? So, and one counts only nearest neighbors. So if it is far away, it is not counted. So this is also a simple equation. The only challenge is large number. And in case there is a magnetic field, one subtracts summation of each spin times value of magnetic field, right? So so it's clear about the energy. What is Z? Statistical sum. For state number I. I think after first part of the class you should be. So it's something both manage, right?
Population.
Yes, but how to write it in equation? So e to the power minus energy of the state divided by Boltzmann, right? And in the denominator, to have it normalized, one makes summation of all possible states and all such terms. Right? So basically, the project is to implement, put right constant here, and just follow the stuff. And you see through this dependence of temperature, there will be the energy will depend on temperature, and when you take derivative, there will be some continuous curve, capacity over temperature. So you already see that there is a challenge, and for some problems like this, there are analytical solutions if something is really symmetric. But here the lattice is not square, is not what we typically do as little rectangles in the notebook. So it adds additional feature. And just to answer this question, one needs a numerical effort. And there is another challenge. So suppose I am a blind researcher, blind not like with eyes, but blind, not very sophisticated. So I take these equations and I start implementing computer code, or just asking someone to write a computer code for me. Just counting all possible spin orientations as I did here, computing energy for each of the spin orientations, plugging into and just literally screening for each value of temperature. As soon as we get beyond this 25, so our cell phones and computers do approximately 1 million operator per second. So this one will be about half minute. But you see how it escalates. If I take a little bit more atoms, computers will fail. So there is no way, and it is only one value of temperature. Then one needs to chop temperature for different values and repeat it, repeat and repeat. So there are tricks to avoid it with something different. And the way to avoid it is the Monte Carlo, which means one takes not all configurations from statistical sum, but only random. But if there are many configurations that have similar energies, if one takes sufficient amount of representative examples, the overall result will not be changed. So if you take not all terms, but randomly pick some of them, the curve will become a little bit noisy. So it will be, but it still will be the same trend. And this is what can be done even for quite big systems. Whew, enough. I'm going to erase and go back to our preferred subject of the lecture. what are the benefits not only for learning but for like in organic chemistry you see connection to metal-organic complexes, right? For organic, well, of course, everyone learns more details about statistical and heat capacity, but there are additional features, like if one goes beyond just heat capacity from the system, that are helpful in creating of quantum computers, and one modifies this material. But modifications are, on one hand, the chemical synthesis, how to do similar lattices with different implementations, and another, just to tailor the substrate. So one of the example, if one deposits this thin film on graphene, which is somewhat organic, then it performs better. Enough. Last time we finished by drawing this squeezed diamond in PV for Carnot cycle, right? And for the upper and lower sides, the PV equals constant, right? And ideal gas state. And we need an equation for this lines 2 to 3 and 4 to 1, which needs to have different curvature. So the question is equation for adiabatic compression and expansion. So the gas has energy of all molecules inside moving, right? So molecules inside gas, then one can call it internal energy, which is not very successful naming, but it means that molecules are not excited, there are no additional transfer, so internal. And the internal energy can be taken from the ideal gas equation of state if molecules like only have kinetic energy, right? And there is a factor 2/3 if it is a monatomic ideal gas. So this 2/3 factor appears from the fact that U is counted as summation of kinetic energy of all degrees of freedom, X, Y, and Z. And for pressure, one needs to count only how the molecules bump into the one wall. And 3 is one takes all degrees of freedom and then select only one of them. And when we meet after the break, I'll probably waste your and my time on rederiving this equation, which is basically a high school equation, but maybe we can revisit it. Now, if so, this factor 2/3 and 2 comes from denominator of kinetic energy, so one needs to remove those. So this is for one monatomic ideal gas. How does this equation change if it is like diatomic, stereoatomic? Would you agree that something happens to the factor? Okay, so there is a convention to tell that this factor will be replaced by gamma minus 1, and this gamma later we can discuss, but since you are doing thermodynamics again and again in your career, you know what it is. The relation of which heat capacities? Okay, it is constant volume, constant pressure heat capacities. What? relation. Okay, so but if one puts variable gamma, then it will be more general. And steam engine, which we started from, it has 3 atomic gas, right? Water. So the structures will be different. Now, a little concept. I'm not going to introduce first law of thermodynamics today. First, you know about it. Second, we need to revisit it in more details later. But suppose I am speaking about adiabatic compression or expansion. So the piston goes down and changes volume by this delta V. Right? The area of this piston is A, and pressure inside is P. So what is definition of pressure, or what are units for pressure if you pump the tire?
ATM.
Pounds per square inch.
Yes, right? Pounds per square inch. So can we say that it is force per area? Right? Okay. Now, what is work? Work is what makes me tired, right? But in the context of the class, if we move the piston up or down, if there is some like mass, and if we move it by delta x in this direction.
Force times the distance, right?
Yes. So work is force times distance, and if we change it a little bit, then it is differential. Right? Now, if we have this definition of the pressure, then what is force? Pressure times area, right? So let's plug it in. So pressure times area times change of the position of the piston. Now, what is area times movement, the step of the piston?
TB.
Yes. So it is increment of volume, right? So the work will be pressure and change of volume. Okay. So catch me lying if I do. I hope by now I didn't, but I make errors unintentionally frequently. Okay. Now, the main part of our today's how to say core part of the lecture. Before it was mumbling about project. After I'll try to sustain your challenge about questions. And what is most important today? So before questions, I'll tell by words. So if we are practicing adiabatic compression, our rod and piston are in the dewar, right? So there is no heating or cooling. So on one hand, we are compressing and performing work, or if it is expansion, the gas performs work. But on the other hand, if we compress, the molecules or atoms become closer to each other, they move quicker, collide more frequent, and the kinetic energy increases, and internal energy U also increases. Right? So can you try to say the same in your own words? Crystal? Can you catch what I've taught and express it by your own words, because I don't think I did my job good. Just try share your impression. You can tell it was something about energy and work, right?
Yeah, because it's the work for the piston going up and down
Yes.
based on like the compression of the gas.
Yes. So there is a work because of the motion of the piston, and there is a change in internal energy of the gas inside.
Yeah.
So here is the equation will be so simple, so short that it can blank through our focus immediately, and no one will remember about it. So, John, would you like to try?
So if it's adiabatic, it means heat can't enter or leave. So the work is proportional to the change in internal energy?
Yes. Yes, exactly. So change in internal energy is minus work. And this is the main thing for adiabatic compression. Main logical, intellectual thing. And the main outcome, the main goal that I'm pursuing and where we will arrive very soon is a mathematical equation for this stuff, which will look like P V in the power gamma equals constant. So I need to make mathematical connection from this statement to this mathematical outcome. Make sense?
Is it the same gamma as the?
Absolutely, yes,
Okay.
yes. So how do I go there? What are the options?
Do the derivative
Yes.
by like plugging in the values that we had, because we said earlier that PV is equal to 3/2 U.
Oh, thank you.
And then
I give credit to your intellectual strength and education, or combination of both. Absolutely correct. I do not know what I'm doing here. You can teach this material.
no.
Absolutely correct. Let's plug in this expression that we got through hand wavy arguments, and I will try to prove it when we meet after the break, and follow the consequences. So I keep the letter D, then I put here PV, and I write it minus P dV. So if I was taking calculus at some point, I can consider this as a product of functions and practice differentiation of product, right?
Do we need? Oh, sorry.
Please, Crystal.
We lost the gamma minus 1. We just got PV, but no. Oh, wouldn't it be PV over gamma minus 1 for you?
Yeah. Thank you so much. So everyone who finds my error gets an extra credit. So Crystal plus 1. Thank you. It is critically important. It will not work without it. Okay, so what do I do with PV? So dP times V plus P dV. I keep this gamma minus 1, right? And it is equal minus P dV, right? I didn't lie up to now, except that I forgotten gamma minus 1. Thank you, Crystal, for saving me and the whole class. So what are we going to do? How do we interpret this equation, and what we are going to do with it? What is the plan to solve it? Which category of equations does it belong to?
Pressure doesn't change.
Pressure may change. No pressure may change.
Sì, ma Dina che sound mi tre
Well,
Oh, never mind.
repeat.
Rational function?
No. I would say it is differential equation. And for question of payment, so the stuff here is a definition. If there is a small increment of the volume, then we can approximately consider that the pressure is not changing on one hand. So this thing, work, and this thing, change of internal energy, are considered independent. I see your confusion when I was preparing and trying to rederive it in the silent room. I also got the same impression. It looks like there are two things on the opposite sides, and why there is no change of pressure here. But it comes from the definition of work. So work is defined only through change of the volume. And here we just practice differential of the product. Thank you, Payman. I'm with you. I was thinking the same direction. Now, this is differential equation, right? So please let me know by like yes or no if you were taking differential equations in the past or taking right now. No, yes, other yes, yes.
Yes, but it's been a decade.
Yeah.
Oh, your knowledge is much more fresher than mine. I was taking it in 1993. So basically, in differential equations, we have this little derivatives. If you form ratios of them, it will be like differentials. And the goal is to get rid of differentiation by integration, right? Integration and differentiation are opposite operations. And we already know the answer. We need to get stuff like this, where we do not have differentials. We have just continuous function. So in regular algebraic equations, the answer is a number. In matrix equations, the answer is a vector. In differential equations, answer is a function. So let me circle this one, and I'm going to release space. I'm going to erase everything except this one, and then I will start over from the top, so that otherwise it will get too messy on the board. And if I go to other side, it will be too much of flipping the camera. But once again, dv dp plus p dv divided gamma minus 1 equals minus p dv. So I can multiply left and right by this gamma minus 1, right? So just v dp plus p dv equals minus gamma minus 1. So maybe I'll open the brackets at the same time. Minus gamma p dv plus 1 times p dv. Right? Can we subtract the similar terms from left and right part?
Yeah.
So we subtract p dv from left and right. Yes? And we are getting v dp equals minus gamma p d dv. So what do we do next? What creates this? Why we are not happy? Why it is not yet answered? And I corrected my own error. No one got a point for this. Okay, so volume and pressure are independent variables. And I don't know about you, I do not know how to integrate simultaneously in two independent variables. But I know how to integrate about one. So it will be really good if we consolidate on one side everything about P, and on the left everything about V, including both differential and function itself. Is it possible to do? How?
You can either divide the differentials to get them switch sides, or you can divide the actual V and P.
Yeah, thank you, John. So divide all, both parts by PV, right? So if I divide left part by PV, V will cancel and P will go into denominator. If I divide right side by PV, P will cancel and V will go into denominator. Make sense? I'll do it slowly by surely. So we do not. So I write V dP divided by PV equals minus gamma P dV divided by PV. So there are no mathematical theorems forbidding me to multiply or divide left and right part of equation by the same function or same number, right? So it is a legitimate operation. I can always do it. So nothing changes if I divide or multiply left and right by identical operation. Crystal, do you have any protest?
No, I just got a little confused. I didn't know you could divide out when it's like a derivative with like P derived with respect to V. I didn't know you could divide out PV, but well, yeah, I believe you. I just
okay, thank you.
I thought you were going to integrate or something.
Yes, right. And it is not derivative, it is differential. Now here let's cancel P, here let's cancel V, and then we have dP divided by P on the left minus gamma dV divided by V. So what is the next step? How do we process equations like this? Right. So I can integrate left part over momentum, not momentum, pressure, and right part over volume. Right. So what is integral if we have like dx divided by x? So please write down what's the result, and I'll go and watch. So you do not confuse each other or do not give too much help. Your name starts with letter F.
Yeah, Faiz.
Faiz. Faiz, can you? A little interview. Can you explain what is the result and?
So the result is ln x plus 1 over x.
Where ln is what?
The logarithmic
function.
Yeah.
Okay. Yeah. Thank you. Thank you. So everyone agrees, right? Log ln. So what's constant? Is it a big surprise for someone, or it is natural? Because it is a natural logarithm.
One of the few laws.
So the 1 over x goes this way, right? And the integral is area under curve up to a certain point, right? So if we integrate at the initial portion, we are getting it in, since it is very high, it gets incremented very, very quick. And as we go to x equals infinity, it starts to slow down. And the constant is just selected somewhere here. So this is 1 over x, this is ln x. Make sense? Okay, now let's practice it here. So it will be logarithm of pressure equals minus gamma logarithm of volume plus constant, or we can tell logarithm of constant. In rigorous mathematical sense, it is already the answer. But for us as natural scientists, it's not very comfortable. We need to just wrap it in more comfortable way. So a little question: why human civilization designed logarithmic function? What's the reason?
Why?
Yes. Because all science is not made with purpose to torture young brains. It is made by humans for humans to solve some engineering problems or.
With big numbers.
Yes, big numbers.
What's your question again?
Why do we need logarithms? What and
A large number to like small ones to be like.
yes, in your research lab, if you do some instruments get measurements, you can plot data in log scale if there is a big range. Yes, good, perfect. And another thing.
Sound intensity?
Yes, decibels. Yes, yeah. I like this class. So, do you ever saw or heard about logarithmic ruler?
Logarithmic what?
Logarithmic ruler. I'll probably bring up Wikipedia next time, or you can look yourself. So write it down. So logarithmic ruler. Ruler, not like emperor. Ruler like a device to draw lines. Yeah, yes,
Like this one?
yes. So if you read Wikipedia about it, you'll be pleased. It was a replacement of calculators and computers not long ago, like 50, 60 years ago, more popular than abacus and more powerful than abacus. So the goal of logarithm is not only describe sound and do big numbers. It is also to replace multiplication by addition. Because addition is something that each of us can do more or less adequately and correctly. And multiplication for big numbers is more complicated. So the main property of logarithm comes from exponential EA times EB equals EA plus B, right? And if we convert it into the logarithm, what are we getting? Let me do another example, which will be very, very simple, so that even my brain that is going to old age will absorb it easily. So what if I take logarithm of the number e to the power 1? So definition is to which power one needs to take the number e to get the argument of logarithm, right? Now, if we have logarithm of e to the power 2, what's the answer? Yes. Okay, now next little example. If I have logarithm e plus log in power 1, logarithm e power 1. So it will be
2.
Yes, but before it is 2 logarithms of e to the power 1. It is, yes, you are correct that it is 2. But at the same time, yes, exactly, it is logarithm of the e to the power 2, right? So if we have gamma logarithm e, it will be logarithm e to the power gamma. Make sense?
Yeah.
So let's practice this property in theory. I'm going to erase these basic things and continue. So here we can put it minus gamma, no, not gamma, minus logarithm v to the power gamma. And we will need, we already coming to what we need. Then we can move it to the left side. So logarithm p plus, so sign is flipping when we move here, plus logarithm v to the power gamma equals logarithm of constant. So what is summation of logarithms? Yes, it is logarithm of product. Ln of p times v to the power gamma equals logarithms of constant. And now we can put little e here. So suppose that it is a e to the power of stuff on the left, e to the power of stuff on the right. And then we by definition of that logarithm and exponential are compensating opposite functions, we get p times v to the power gamma equals constant. So I'm almost done. I want to just redraw the figure. Basically, this is answer for adiabatic compression or expansion. Adiabatic. So the overall motivation to study this process and to derive this function was to get steeper curves in the Carnot cycle. So let's make a little experiment, not as advanced scientists like you are doing, but simplified numerical experiment with numbers. So I do have two functions. PV equals constant and PV to the gamma equals constant. And the gamma, the value of gamma is what? So if gamma minus 1 was 3 halves, for monatomic minus 1 was 3 halves.
Was it 3 halves or 2/3? You said 2/3 earlier.
Yes, yes, thank you. The crystal plus 1 once again. Thank you. Thank you for saving us continuously. 2/3. Then gamma will be 2/3 plus 3/3. Right? So will be 5/3. Okay? So P times V to the power 5/3 equal constant. Right? So I hate units, but let's just design our PChem units which will be dimensionless for quick experiment. So volume will have two values, 1 and 2, and pressure will take value 1 and whatever it takes. So suppose we select constant equals 1 in both cases, and both points. So for isotherm, it will be point. For adiabatic, it will be close. So if you select constant equals 1, then for volume equals 1, pressure will be equal 1 as well. Okay? Now let's explore this isotherm if volume equals 2. Where will be the point? So volume equals 2, P will be equal 1 divided by 2, right? So here and there, I put 1/2. And it will be 1 over volume curve. Now, will the second curve be steeper or shallower? Let's just plug in. So P equals 1 divided by 2 to the power 5/3. So 2 to the power 5, we already tried it, will be 32, right? And then we need to take root of the third order. Suppose I do not have calculator. So 1 to the power 3 is 1. 2 to the power 3 is 8. 3 to the power 3 is 27. 4 to the power 3 is
315.
64. And answer will be between 27 and 64. So it will be 3 point how much?
I got 0.315.
Okay, 0, not 0, 3.
Oh, I think she's talking about the 1 over 2.
Oh, yes. But it will be like something like 3.1.
Oh,
So 1 divided by about 3 point, or maybe 3.2. And then it will be like 1/3. 0.315? Okay, I believe it. So it will be 0.315 here. So it will decrease with volume more steeper, right? And it is basically the positive outcome of our meeting. We were not putting more ambitious goals rather than prove that for adiabatic compression and expansion, we get steeper dependence of pressure and volume. By the way, if instead of monatomic gas like helium, if we use in our steam engine like oxygen or nitrogen, the steepness will increase. If you use 3 atomic like water, it will increase further. If you use alcohol, which has so many atoms, it will be even better. So probably one needs to do steam engines on alcohol. So I'm done with this material, and so I'll give sign to the camera. Lecture is done.